The topic which we are going to discuss in this video is actually not really connected to stochastic or deterministic processes and signals, but it fits here very well because we want to describe quantities like power quantities or other physical quantities. And for this, we use the decibel to simplify the description of these quantities. So imagine that we have a system here, which so this is a simple communication system which consists of a signal generator, an amplifier, an antenna which transmits the electromagnetic signal, which propagates in the free space, and then it is received by a receiver. And now we generate a signal with a power of 2 milliwatts here, and then the amplifier amplifies it up to 4 watts with a factor of 2000, and the antenna radiates the signal with a power of 4 watts, and the free space path loss attenuates the signal on the way to the receiver, and the power at the receiver is 60 nanowatts, so it's very, very low compared to the 4 watts at our transmitter antenna. But to make it usable, the receiver again has an amplifier which amplifies the 60 nanowatts to 500 microwatts. So you see here very huge factors that we have to deal with, and they are a bit unhandy. So remember back to chapter 2 where we discussed transform in general. So we have a problem here in the linear space. What it is, we will clear that later, and it is rather difficult to solve in the linear domain. So actually you can say, yeah, it's just a multiplication by thousands and just a division by 250 million. Yeah, it's not a big deal. So modern computers can solve this without a problem. But we will find a representation of the same problem which can be solved more easily and has some benefits. So let's say the multiplication is a difficult solution compared to the solution which we have here in the logarithmic scale. So we use a logarithm transform to transform our problem to the logarithmic domain or scale, find an easy solution and transform it back. So how does our easy solution look like? So it's the same problem here, but described in the logarithmic domain. So for the logarithmic transform, what's the basis which makes it more easily is this equation. So we can decompose multiplication in the logarithmic scale into an addition. So let's see what this means to our example. So this is our example from the slide before in the linear scale, and now we transform it to the logarithmic scale, and what we see is, for example, consider the 2 milliwatts here, and we use this transform and obtain a value of minus 27. And now we take the 2000 and apply the same transform, which is given here, and we obtain a plus 33. And now if we add it, we obtain a 6 here. And now continue with the other steps. So here for example, the division by 250 million becomes a minus 84, and so on. And in the end, we obtain here as a final result minus 33, and now we can back transform it and get 500 microwatts. So what happened here? So the logarithmic transform converted the multiplications to simple additions, and something more happened. So our very unhandy huge values like 250 million just became very handy values like 33 here, or minus 84 or plus 45, and these values are actually very handy to deal with. So you don't always have a computer to calculate systems like these. Sometimes you just want to make a quick overview as an engineer on paper or something like that, and for this purpose it's better to deal with quite small numbers like 33 and 84 and so on, so you can get a quick overview of your system and your signal powers involved in the system. So this is why Decibel is still very popular in radio frequency engineering and other fields of electrical engineering, because they are so easy to deal with without needing a calculator or a computer. And there's another benefit. For example, we have a time domain signal here. It's our rectangular signal. You know it from the second lecture. And now we take the Fourier transform, which looks like this. And here you have a maximum and then some side lobes, and the side lobes get weaker as the frequency increases. And here in high frequency parts, the side lobes are so small that they are very close to zero. So if you display them in linear scale, you cannot see them anymore because they are so close to zero. They just look like a flat line, like here. But they are still present, and you need to know that there are side lobes because you want to analyze the signal, or you want to check that the signal fulfills some parameters or something else. So you need the information that there are side lobes, and you need a kind of quantity to say how strong the side lobes are, but you can't in this case because they are so close to zero, and therefore the frequency domain representation can be transformed into logarithmic scale, and then we have a different picture. There's still a maximum here, but we can very easily identify our side lobes, which would be very close to zero. But here in linear scale, we can see them. We can still see them. And for example, divide the scale here. So this is maximum 1, and because it's logarithmic, more zeros are added in between and so on. So you see that the signal here, the side lobe here, which would be 0.001, are still present in this diagram here, which would be which would disappear here because they are so close to 0. Yeah, here. And so on. So here for some examples. So the decibel is calculated here by this formula. You will find a more detailed explanation in the lecture notes, chapter 3.2.4. And here are some examples. Let's say x equals 10, and we have 10 decibel. So decibel is the unit used here to show that the value 10 here is given in logarithmic scale. Yeah, so 10, logarithm of 10 is 1, multiplied by 10 is 10. 100 is 20 decibel, 0.1 is minus 10 decibel, and so on. Again, if you would, for example, take 1000, then that would be 30 decibel. So the step from here to here and from here to here are always just plus 10 dB, and this actually means multiplied by 10 in linear scale. And there are other examples, for example from 20 decibel to 23 decibel, there's just an increase of 3 decibel, and in linear scale that means a multiplication by 2. So this means from 100 to 200, and this can be used to describe actually any value. For example, 400. What's this? You can decompose it. 2 multiplied by 2 by 2 and multiplied by 100, and you can further decompose it. And you know that 2 means 3 dB, and multiplication becomes a sum. Now 10, a multiplication by 10 means 10 dB. And here we go. These are 26 dB. So 400 is 26 decibel. Yeah. And we can also continue this with this example. So in linear scale you need to divide 0.1 by 2, and division by 2 means minus 3 dB. So this is one of the benefits of the logarithmic scale, that multiplication become additions, and it is possible to show very, very weak signals, which are just very, very small fraction of some other signal in the same diagram, and you can still see it. It maybe takes a while until you get used to the logarithmic decibel scale, but it's worth to learn it. And so far we have considered decibel to describe factors or multiplications, but it is also possible to display physical units in the logarithmic scale. For example, we have 2 milliwatts from our previous example. What is it in logarithmic scale? So we need a reference, and now let's choose 1 milliwatt, and you know that our reference is 1 milliwatt multiplied by 2 yields 2 milliwatts, and here we have to explain this, our reference, let's explain it this way, it's 1 milliwatt multiplied by 2, and this means in the logarithmic scale our reference is always 0 dBm, or here this means 1 milliwatt is 0 dBm. Here it would mean that 1 volt equals is equivalent of 2 dB volts, and so on. This is just a convention. And now here, and we can use this and our knowledge from the previous slide that multiplication by 2 is just 3 dB, and this yields 3 dB. Okay. Same goes for the 16 nanowatts, which are nanowatt is 10 power minus 6 milliwatts multiplied by 2 by 2 by 2 by 2, and this means minus 60 dBm plus, let's take a shortcut here, no, yeah, which means minus 50, no, it's minus 48 dBm. So this shows the benefit again. So here you have 3 dBm for 2 milliwatts, and here you have minus 48 dBm for 60 nanowatt. So it's more easily to compare the two power levels. It's easier to compare a 3 with minus 84 than comparing 2 milliwatts with 60 nanowatts. So this is why we prefer using decibel units rather than linear units